Dear students, in today's lecture we will discuss chapter 9 of the textbook, which discusses single phase and special purpose motors. The two sections which we will cover in this lecture are the universal motor and the stepper motors, brushless DC motors. So first of all, as we discussed in previous classes, a simple architecture of a DC motor. In this diagram, the colors are quite helpful. That red color is showing the electric current passing through the loop in red color. In blue color, the magnetic field B is represented, and the magnetic force F is represented with green bold color. So when electric current passes through a coil in a magnetic field this B, the magnetic force F produces a torque which turns the DC motor. So this loop moves because of this force, and this formula for this force is ILB. F is equal to ILB. Now we want to discuss the universal motor. That what is a universal motor? A universal motor is basically a DC motor and connected that DC motor with an AC source. In that case, we can make a motor a universal motor because the motor is eligible to perform under DC source as well as AC source. That's why it's called universal motor. Now we will discuss some points. First of all, this is a basic diagram which shows a universal motor with internal voltage EA, resistance and inductance, and this is the terminal voltage VT. Now we discuss some few points which clarify the structure and working of the universal motor. If the polarity of the voltage applied is reversed, both the direction of the flux, field flux and the direction of armature current reverses. Now we know that this voltage, in this case the flux and the current, these are the two main variables. If both of them reverses, then the resulting torque continues in same direction. It means that tau induced is equal to K into this field flux into this armature current. So if field flux and armature current both are reversed, then minus minus would be positive and the resulting answer would be positive, or you can say the resulting torque continues in the same direction, or it is not reversed. Therefore, it is possible to achieve a pulsating but unidirectional torque from a DC motor connected to an AC power supply. So we can get a unidirectional torque from this phenomena. The design is practical only for the series DC motor, since the armature and field currents must reverse exactly at the same time. For shunt DC motors, it is not possible to reverse the currents at the same time. So for shunt DC motors, the very high field inductance tends to delay the reversal of the field current. Because of this high field inductance, it is not possible to reverse the field current abruptly or instantly. It delays this procedure and reduces the average induced torque of the motor. In order for a series DC motor to function effectively on AC, its field poles and stator frame must be completely laminated. So there should be a complete lamination on the poles and on the stator frame. If they were not completely laminated, their core losses will be high, or you can say will be enormous. When the poles and stator frame are laminated, this motor is called universal motor, since it can run from either an AC or a DC source, as we discussed earlier. So that's why this motor is called a universal motor. The universal motor has a sharping, drooping torque speed characteristic of a DC series motor. Like this is a sharply drooping torque speed characteristics. This is speed on y-axis and torque on x-axis. So this torque speed characteristics is quite abrupt and quite sharp in series DC motor case. So that's why it's not suitable for constant speed applications. So the universal motors are used where lightweight and high torque are important. It is compact and gives more torque per ampere than any other single phase motor. The main applications of the universal motor are vacuum cleaners, drills, and kitchen appliances. Now we come to know about stepper motors. Now we want to discuss the stepper motors, in which the motors are not rotating in a go, but they are rotating in steps. So if a motor wants to rotate 360 degrees, it will rotate in few steps, not continuously. So these steps would be controlled by this V controller, and this is the voltage applied on the input. On the control unit is connected with the windings of the stator of the motor. So there are a three-phase motor, three windings, and the rotor field direction shown is in the right side in this case. So these are the glitches on which the decision would be made, or we can say on these points, on these cycles, on these points, uh, the motor, the rotor turns for some degrees. Let's suppose if we want to rotate our rotor for 30 degree, or for one step of 30 degree, then it will be rotated for 30 degree, then again for 30 degree, then again for 30 degree at each step. So 8 steps are shown over here for different time intervals, and the input pulses are different, like VA is 1 at this first pulse. At first pulse VA is 1, VB is 0, VC is 0. So similarly you can see at pulse 1 VA is VDC, VB is 0, VC is 0. At pulse 2, this is pulse 2 starting. At this point this A becomes 0, VA is 0, 0, VB is 0, 0, and VC is minus VDC. You can see minus VDC. So in this scenario it can be seen that the rotor is rotating in steps. It can be seen from this diagram that if at first pulse A is VDC and BC are 0, then A winding A bar is this loop, and the magnetic field would be something like this. Similarly, in another case where A and B windings have 0 and C have minus VDC voltage, then this would be the direction of BS and BR. So this is 60 degree shifted from the previous case. This is 60 degree shifted from the previous case. Now we want to talk about the brushless DC motors. There are many DC motors applications where we need there should be no any contact brushes, so that there should be no any maintenance required, or no any uh, wear off. So in those applications it is desired to have a DC motor which is brushless and don't use the brushes to complete the circuit. The basic components of a brushless DC motor are a permanent magnet rotor, and this works in a kind of motor. A stator with a 3, 4 or more phase windings. In this case these are 4 phase windings. A, B, C, D, 4 windings. A bar, B, B bar, C, C bar and D, D bar. So A, B, C, D. A rotor position sensor is connected with the control unit in this case, and an electronic circuit to control the phases of the rotor winding. And this is the complete circuit which is used, especially this unit, which is the control unit, which is used to control the phases of the rotor windings. So this is how the A, B, C and D phases and windings are working. On the x-axis there is time, and on y-axis this is the voltage, how the voltage is, like it can be seen that this is 1 0 0 0, then 0 1 0 0, then 0 0 1 0. So it can be easily be implemented in the applications where small motors are used, or the applications where changing the motors or changing the brushes is quite difficult after some time. So in those applications it is desirable to use brushless DC motors. Thank you.